Okay, here we are at the cellular signaling at chapter 16 again. Um, so this analogy is highly used by the engineers. The black box, there is an input, there is an output, and what happens inside is, we don't know. It's a secret. We don't know how it is calculated. It happens like in the microprocessors. It happens in some softwares, and in our case, it's nothing but a cell. So in this case, the input is the signal. The signal is taken by the cell. There is an output which can be differentiation, which can be cell division. The output can be, let's say, movement, proliferation, suicide, whatever, but there's an output. And we simply what is going on inside. We simply don't know what is going on inside. Because there are more than 200,000 different proteins in the cell and a good amount of different RNAs, non-coding RNAs. The interaction between them is extremely complex. So what is really going on there? What is interacting with what? How is the decision taken? We simply don't know. This is a big problem in biology. One of the things that the biology wants to solve, or we have to solve immediately, but it looks like it's going to take too much time, because this black box is really dark and we are trying to put light on some specific interactions, but even finding these specific interactions, simple pathways, is taking like years and years. So, this is a hypothetical pathway of what is going on in a cell when the extracellular signal is received by the receptor on the cell surface. And it is received on the cell surface because the signal is either too big or too hydrophilic, so it cannot pass through the membrane. This is going to relay the signal, and remember, this thing is called signal transduction. See, the signal is received in one way and it is converted into another form. So it's again a chemical, but the signal received from the outer environment is different from the signal that is expressed in the inner environment, the intracellular portion. And signal transduction, you can imagine signal transduction like your cell phone. It is receiving the electromagnetic signal. This electromagnetic signal is, of course, not voice. First, it has to convert this electromagnetic signal into voice so you can hear the voice of the person that you're speaking with. That's a form of signal transduction. What your television is doing is a form of signal transduction, and in this case, what the cell is doing is converting one signal type into another signal type, which is actually a signal transduction. So these first steps are more or less clear, but the steps under the pathway, below the pathway, they're quite complex. So you can have many intracellular signaling molecules, and at the end of these intracellular molecules, this is a black box, we don't know what is happening. It can activate some metabolic enzymes, so the metabolism can change. You can start to burn fat, you can start to gain fat. The cytoskeletal proteins can change so that the shape of the cell changes. It can be a white blood cell eating a bacterium, or it can be a virus infected cell interacting with the environment, or it can change the gene expression profile. Think about your growth in the adolescence. Your body start to produce more and more hair, more muscles, you're growing, etc. These are all due to some changed transcription factors. And if we check in more detail, there are many things that is happening. There are many different possibilities. So, one possibility is that when the signal comes here, the signal will be simply relayed. So it will be relayed from this molecule to this molecule, this molecule to this molecule, and I don't know why, but it simply relates. Of course, this is a membrane protein. It cannot move, but these proteins are also stacked on a scaffold protein. The scaffold proteins are large and they are holding many proteins together. And in this case, they are simply transmitted from one protein to another. Simply, for some purposes. Is possible, and in some other cases the signal can be amplified. So in this case, for example, this one single molecule receives the signal, and at the end it is creating lots and lots of other effector molecules. This is very similar to actually guanylyl cyclase. That's actually the same thing. Guanylyl cyclase enzyme producing cyclic GMP from GTP. So when the guanylyl cyclase is active, it is not going to create one signal cyclic GMP, it's going to create thousands of them. And this is an example of amplification. This is one thing. And this is very useful because the signal molecule, like the hormones or the the single molecule that you take from outside, is just one single molecule. Maybe two, maybe three, not much. But if you want to react to the signals in a good way, you cannot wait for the other signals. You just have to get the signal seriously, and you should amplify it so that everybody in the cell will hear the signal and everybody will react it for signal. And the second thing that once one molecule doesn't usually receive one single signal, it is taking several signals. Check, it is combining three signals, maybe that is coming from three different pathways, and it is integrating these signals. So integration is a common thing. And this is also good because different information, different pathways in the cell, they have to communicate and they have to make a common decision. Now think about a cell that is going to be dividing soon. For the cell to go under mitosis, it has to check several things. It has to check if the surrounding cells are okay with that, if the body is okay with that, if there is enough food, if there is enough surface, if there is enough protein, if there is enough, let's say, if the unfolded protein response is too high, it's not going to divide. If there is not enough phospholipid production, it's not going to divide. If there is any problem with the DNA replication, if there is any mutation, it's not going to divide. In such a case, for example, one single decision molecule, like a microprocessor, it has to integrate all the information coming from different pathways, and it has to come up with one single decision. And in other cases, one single molecule, it can affect several things at the same time. Now imagine again a cell wants to decide, it is starting the S phase. The checkpoint between the G1 phase and S phase is broken, so it's going to start the S phase. At this point, several things has to happen at the same time. It has to start growing, it has to start DNA replication, it has to check the DNA quality, and it has to check the organelles for the common stages. So all these jobs are different jobs. They have to require activation of different signaling molecules, and they have to be controlled. But in this case, one signal key molecule are controlling many of them at the same time. Okay. Now, this black box is very difficult to solve, but that is the purpose of many studies, including proteomics, transcriptomics, developmental biology. In developmental biology, we are trying to understand how one-to-one molecular interactions are shaping the tissue, how one molecule can be important for the differentiation of one tissue. For example, in my case, I'm checking if one single molecule can create cancer or it can create tissue growth, etc. Now, I'm going to describe some pathways, feedbacks that is commonly seen in biology, positive feedback loop and negative feedback loop. Now, these feedback loops, they are actually common to many things, even in chemistry, even in physics, you can see them, but I'm going to describe them in the context of biology. Now, there are two things to proteins X and Y. Now, X protein is activating Y protein. Maybe it is inducing a post-translational modification, but in this case, we are assuming that it is increasing its transcription. So it's acting as a transcription factor. This is good. We see so many things like this, but this Y protein also induces the X protein. Now we see a loop because it is circling around. And this is called a positive feedback loop. Let's make Y blue. Okay. Now check their levels. So as the time goes by, check how the protein levels are affected. So at the beginning, both X and Y are 0. So as the X starts to increase, it is going to activate Y because it is increasing Y. So the Y protein will also start to increase a little bit later than that. Now, because the Y protein is also activating X protein, it is going to create more X. And because X is inducing Y, it is going to create more Y. Again, because Y is inducing X, it is going to create more X. And because it activates Y, it's inducing more Y. And it is going to go unlimitedly. In theory, of course, in practice, it's at one point it's going to reach to the plateau because the resources will be used up. But this is going to be an increase. This is going to be a sharp increase because as there is more X, there will be more Y. As there is more Y, there will be more X. The viral pandemic also moves this way. As there are more patients, they are going to distribute the virus to more people, and there are going to be more patients. So at the beginning, there's going to be just few amount of patients, and then it increases sharply. This is also a form of positive feedback loop. Another one is the negative feedback loop. In this case, there's the protein X. Yes, it is helping the protein Y. Protein X is a good protein. It is helping a lot to protein Y. But protein Y is kind of mean. It is a selfish protein and it is negatively regulating protein X. So this is not a positive feedback loop anymore. This is a negative feedback loop because as there is more X, it is going to activate more Y, but Y is going to suppress it. So let's see the graph. This is time and this is protein levels. Now, let's say we have 0x at first, and then the level of X increases with some other mechanism. When the level of X increases, of course, because it's inducing Y, the level of Y will also increase. Now, what happens when you have high levels of Y? It is going to suppress X. It is not going to help X. This is why the level of X will decrease. And when the level of X decreases, because Y protein requires X protein, the level of Y will also decrease. And when the level of Y is low, because it cannot stop X anymore, the X will be free to increase again. So when it increases, it also helps Y to increase. But again, when Y protein is too much, it is going to block the X protein, so the X protein will decrease again. And because it is not induced anymore by the X protein, the Y protein will also decrease. So this is called oscillation. And they are very helpful because it prevents a sharp increase, like in this case. These sharp increases, they are very helpful for the virus in a viral pandemic. They are very helpful if you are giving birth to a baby. But for other cases where you need to keep a balance, where you need to keep a steady level of the proteins, they are going to oscillate. And this oscillation is very helpful, especially for circadian clock. If you want to go check, the circadian clock works exactly this way. And there are many things like the blood sugar levels, they are controlled this way. They are kept at a steady medium level, because keeping things medium in a usable manner is also important.